Here are solutions to homework set number 12 for ECE 461-661 control systems. This homework set looks at Bode plots, Nichols charts, gain and lead compensator design in the frequency domain. The first problem is, given the gain versus frequency, the blue line, what's the transfer function? Well, the trick here is to draw asymptotes at multiples of 20 dB per decade. So that'd be the first orange line, that's 0 dB per decade. The second one dropping off at minus 20 dB per decade. And the third one dropping off at minus 40 dB per decade. What that tells you is where the two intersect at a corner, that tells you there's a pole. So here I drop by 1 factor 20. There's one pole at about 1.8. There's another pole at about 17. So it tells you that the transfer function is roughly some gain over s plus 1.8, s plus 17. To find k, pick your favorite frequency. Like at 0.1 radian per second, the gain should be 7 dB. So plugging in s equals j.1, solving for k is about 68, so there's g of s. Problem 2 is repeat. Here's a curve at the blue line. Find the transfer function. To do that, again, I draw the straight line asymptotes. Here's one at 0, this one's at plus 40, minus 40. Where they intersect, the corner is your pole location. So here I start out at plus 40 dB per decade, so I've got two zeros to the left of 0.1, probably at 0. So that's s squared. I've got two poles at about 0.6 radians per second at some angle, and two poles at 20. To find the angle, I find the gain at the corner. So here the gain at the corner is up about 4 dB. Here the gain at the corner is up 0 dB relative to the corner. That tells you the damping ratio. So 1 over 2 zeta is the gain at the corner. 4 dB is 1.58. Solve for zeta. Zeta is 0.31. Our cosine 71 degrees. So this pole is at 71 degrees. The pole at 20, gain at the corner is right at the corner, up 0 dB, or 1. 1 over 2 zeta is 1. Zeta is 0.5, or 60 degrees. There's the second pole. I've got two zeros to the left of 0.1, call it 0. To find the gain k, pick your favorite frequency. Like you could say at 2 radians per second, the gain should be about 3 dB, or 0.1 radian per second, gain should be minus 30 dB. 100 radians per second, gain should be minus 26 dB. Pick your favorite. Then find k to max the gain at that point, and you wind up with a number like 503. So here's g of s. Problem 3. Problem 3 says, given the gain versus frequency, what's the max gain for stability, and what value of k results in resonance of 1.5? Well, the trick is to take the data and transfer it to a Nichols chart. In MATLAB, I just said, here's the gain in dB, phase in degrees. What that means is g of j omega is 10 to the dB over 20, and the phase shift is e to the j phase. I'll draw the Nichols chart with my M circle. I want to know when is the M circle 1.5, and that gives me this curve. Then it's just guess again, where am I tangent? So this is g, this is k times g. To be tangent, I want k of about 1.7, so that's the gain to make the resonance 1.5. The max gain for stability is at 180 degrees. So here's 180 degrees. That right there is the maximum k. So the biggest k can be is about plus 17 dB. That puts you right at the edge of stability. The best k, or k for resonance of 1.5, is keep away from minus 1 by this distance. The k that does that is this far, about 5 dB. Problem 4 looks at gain compensation. Design for a phase margin. So for phase margin, what you're doing is, instead of being tangent to the M circle, I'm going to intersect right at this point. And the assumption is that with the slope, if I intersect the M circle at this point, that's roughly where the tangent is. The resonance will be roughly 1.5. So for a 50-degree phase margin, I want the gain to be 150 degrees away from unstable, or minus 130 degrees. The trick is to search where is the phase shift minus 130 degrees. Searching the j omega axis, I wind up that the frequency that does that is 2.124 radians per second. At that frequency, the phase is 130, but the gain's off. Pick k to make the gain 1 at that frequency. K is 8. So that's my gain compensator that gives you a 50-degree phase margin. If I find the closed loop gain at that point, here's G, there's K, from the closed loop system. Plot the step response to the closed loop system, and here's what it looks like. There's the step response, here's the DC gain, there's the overshoot. That kind of looks about what you expect. To kind of see what's happening, if I draw the Nichols chart along with the resonance corresponding to 50-degree phase margin, the resonance should be roughly G over 1 plus G. And this is, I'm assuming the resonance is when the open loop gain is 1, and I'm at minus 130. If I draw the M circle at 1 for 1.18 on the Nichols chart, here's what it looks like. So here's the M circle. Here's your GK. And notice that I intersect the M circle right here. When the gain is 1 and the phase is minus 130 degrees, that's what you're doing when you design for a phase margin. If I look on the Nichols chart, I can see I'm actually slightly inside the M circle, so the overshoot's a little bit higher than it should be. If I add a lead compensator in designing for phase margin, what I do in the frequency domain is I cancel not the slowest pole but the next slowest one, put it 10 times further out. Let's see. I then find out where's the open loop phase shift minus 130 degrees, 50 degrees away from 180. That's now 4.2 radians per second. Pick k to make the gain 1 at that frequency. So here's my lead compensator. If I plot the closed loop step response, here's G, here's K, there's the closed loop system, DC gain, overshoot, got 19% overshoot. And here's your step response. To see what's happening, again, it's instructive to look at a Nichols chart. I intersect the M circle right at 0 dB minus 150 degrees. And I just go a little bit inside the M circle, so the overshoot is just about what I expect. On problem 6, if I have a half-second delay, now design a gain compensator. Again, the Bode plots and frequency domain, that's not an issue. I just want to find out where is the phase shift of G times your delay, minus 130 degrees. Turns out that's 1.1 radian per second. Pick k to make the gain 1 there, k is 3.97. So if I plot the step response, in MATLAB I'll have G, I'll use a 6th order Bode approximation to approximate a delay, times k. Closed loop system is G times delay times k, over 1 plus G times delay times k. Plot the step response. You can see that here's your half-second delay. There's the step response. I've got a lot more overshoot than before. The reason for that you can see on the Nichols chart. I again am designing for phase margin, so I intersect the M circle at 0 dB minus 130 degrees, but now I actually pass inside the M circle quite a bit, so I'm getting closer and closer to minus 1. The closeness, moving inside the M circle, also means you have more overshoot. What I really want to do is design to be tangent, but designing for phase margin just designs for this point. If I want to add a lead compensator, same procedure as before, cancel not the slowest pole, but the next slowest one, move it 10 times further out. Now find out where is the phase shift minus 130 degrees. It's now 1.4 radians per second. add that frequency, make the gain 1. So here's my lead compensator. Plotting the closed loop step response, there's G, delay, K. I get this step response. There's my half-second delay. Again, on the Nichols chart, I intersect the M circle at 0 dB minus 130 degrees. That's what you do when you design for phase margin. Again, I'm going inside the M circle a little bit. That means the resonance is too high. That means the overshoot's more than I expect. But that's what you get when you design for phase margin. When you design using root locus, you're a little bit conservative. If I design for 20% overshoot, I'll get a little bit less because the extra poles smooth it out. If I design for phase margin, it's a little bit aggressive. I intersect the M circle, so I actually go slightly in, giving me more overshoot than I expected. If I design for resonance using a Nichols chart, Nyquist diagram, become tangent to it, that's the most accurate way to do it. But by Murphy's law, the most accurate is also the hardest. So that is homework set number 12 for ECE 461-661.